Alright, this video is going to look at what we call definite integrals, and before we get into the topic I want to go back and review quickly where we talked about indefinite integrals, and that was the form of the integral of f of x dx. And if you recall, when we took the integral we ended up with a family of functions. And recall that's because when we integrated, we always had to add on a plus c. Remember that constant term we would always have to add on. So we would end up with a family of curves or a family of functions. And now looking at a definite integral, when we integrate, notice here that we now have these limits here from a to b. We have a as a lower limit, b as our upper limit. And once we integrate, we're going to plug in these limits, and our answer is actually going to be equal to a number. So notice now we're not going to have a function. The definite integral is going to equal a number, and that number can be positive, negative, or it could also be equal to 0. So keep that in mind. And before we look at this, I want to go back and talk about the definition of a Riemann sum. And you can read more in your book about this topic, or you could do a search on the internet. I'm briefly going to cover this definition here to lead into our talk about definite integrals. The Riemann sum here is named after a Riemann, a German mathematician. And if you recall, when we talked about calculating our upper and lower sums, down here notice we were calculating our rectangles, and our rectangles were divided into equal widths. Well, that was actually a type of Riemann sum where each width was the same. Well, what this mathematician Riemann discovered is that the widths here that we come up with do not have to be equal. They could be different sizes. And we're really going to focus on the interval that has the largest width. And what we can indicate here is by this sum of I equals 1 to n f of ci times delta xi, we have a partition, and that's what we're dividing this into. And the widths don't have to be the same. So if we look at the definition of a definite integral, we're going to kind of use this idea from the Riemann sums. It says that if your function is defined on a closed interval from a to b, and the limit here, and the notation here for this partition with these double bars, this is giving you the width of the largest subinterval. So up here I just have two examples. So the largest subinterval up here would be this delta x2. So we're looking at the largest subinterval that we have, and if that approaches 0, what's going to happen to all of the other intervals? If you think about the other intervals, if we pick the largest one, if it's going to 0, the width is going to 0, certainly all of the others must be approaching 0. And we're going to sum this up from I equals 1 to n, and then we have our f of c sub I, and the c sub I is, most of the time here we're looking at the right endpoint of our interval, so here we have c1 and c2, times delta xi. So again, this is very similar to what we did with the upper and lower sums in the previous videos, except for now this is just indicating, saying the width could be different. Now for us, we're usually going to use our width. We're going to think of that as being equal because it's a lot easier for our mathematical computations. And what we're going to look at now though is we want to define. Up here we talked about indefinite, we're talking about a definite integral. We want to transform this to a definite integral, and that's what we're doing here. This limit of our sum can be written as this indefinite integral, which has limits from a to b, and a to b is simply the interval that we've been talking about when we were summing up all of those rectangles before. And now we have our function f of x dx. So dx we can think of, that is our delta x. So the little dx is representing the width of our rectangles. So up here you can think of this as delta x. For the integral we can think of this as dx. Now, I talked about this uh, representing the largest partition here, the largest interval. I prefer to write the limit this way, how we were before. The limit as n goes to infinity. So n, the number of rectangles, if you will, if that goes to infinity, then that means, again, that the width is approaching 0. And then, of course, we have the same f of c sub I delta xi that we had before. And the c sub I that we're using, this is the same thing we did before. We have our a plus delta xi. So let's see if we can apply this to an example. Now, I know I went through this rather quickly, so you can kind of read through your book a little bit more to get an idea of this idea of Riemann sums. But I think if we go through some examples, hopefully that will explain this a little bit better as well. So our first example, we have the integral of -2 to 1 2x dx. And like we did before, we want to use the limit definition to evaluate this definite integral. So we're going to take and transform this integral using this limit definition over here. So we're going to have the limit as n approaches infinity, okay, and the sum we have is going to be I equals 1 to n. Now we need to figure out what is our f of c sub I and the delta x sub I. Well, we want to keep in mind we talked about the width of our rectangles before. Now keep in mind we're going from -2 to 1. These limits would be our interval of -2 to 1. So our width, which would be the change in x, or delta x, we defined as b minus a divided by n. So in this case, we're going from -2 to 1. So that means we would have 1 minus a -2, because 1 is the upper limit, the -2 is the lower limit, over n. So we end up with 3 over n. Two negatives make it positive, so we get 3 over n. And we can really think of this here, again, as really being our dx. So that's kind of representing the small little width dx, because dx is representing this small little width of our rectangle. So for the notation here, that's what this dx we can kind of think of representing. Okay, so we have the dx, the width, which is the 3 over n. Now we need to figure out what is the c sub I. Well, c sub I is equal to a plus the delta xi. Well, the a value we're talking about is for the integral goes from a to b. So our a value is a -2 plus our delta x. Well, we just found delta x here, which would be the delta x is 3 over n. And that's multiplied by I. So this is our c sub I, but we need to find f of c sub I. So that means we're going to take the -2 plus 3 over ni, just like we did before, and substitute all of that in to our function, the 2x here. So all of that goes in for x, and we will end up with 2 times x, which becomes -2 plus 3 over ni. Okay, so now we just plug that into our formula. Well, up here we have f of c sub I. Well, that's going to be the 2 times -2 plus 3 over n I. And then the dx, we found dx, or this delta x, to be 3 over n. So now at this point, here's our limit. So at this point, we're going to do the same thing we did before. We're going to simplify. This is the same process that we did in our earlier chapters. The only difference now is we're relating this to this indefinite integral. And other than that, it's the same process. I'm going to take and multiply here to save a couple steps. We have the 2 and the 3 multiplied. So 2 and 3 is going to give you 6 over n. And then I'm going to distribute the 6 over n to both of these pieces. So therefore, we're going to end up with 6 over n times negative 2, which would become negative 12 over n, plus 6 over n times 3 over n, which would be 18 over n times n becomes n squared on the bottom, and we still have the I. Okay. Now, recall those summation formulas. Remember, we had the sum of I was equal to n times n plus 1 divided by 2. And the sum of a constant was equal to the constant times n. So for our example, we can eliminate the summation. So we still have the limit as n goes to infinity. Now to get rid of the summation, we're going to plug in our formula. So negative 12 over n is really our constant here. So that's going to be multiplied by n plus 18 over n squared. So here's your I. So in place of the I here, we're going to plug in n times n plus 1 over 2. So I'm going to go ahead and distribute the n. So that's n squared plus n over 2. And we're getting closer. If we do a little bit more simplification here, notice the n's are going to cancel. So we'll be left with negative 12 plus, here we're going to distribute, we would have 18n squared plus 18n over 2n squared. Now this is at a pretty manageable point in order for us to take our limit. And if we let n go to infinity at this point, the negative 12 is a constant, so therefore that's just going to be a negative 12 plus the limit as n goes to infinity for the second piece. Notice once again that we have the same exponents on the top and bottom. So we're going to take the ratio of the coefficients, 18 over 2, which would reduce to 9, and then a negative 12 plus 9 equals negative 3. And therefore we have the answer to this integral. The integral of 2x from negative 2 to 1 is equal to a negative 3. So there's the difference with the indefinite where we had a function or a family of functions. The definite integral turns out to be a number, which could be positive, negative, or 0. And in this case, we end up with a negative 3. All right, keep in mind, I know I went through this rather quickly. If you need to, go back and look at this definition of your Riemann sum a little bit. The main reason I was trying to cover this is to lead into the definition of our definite integral, which here we're using this limit definition to evaluate. Later on from now, we're going to look at some other techniques that we can use, but I want you to understand how this limit definition works so that you can see that we're summing up these rectangles. And for this example, the negative 2 to 1 is just representing that interval that we looked at before when we were using the upper and lower sums. And hopefully you can see this process is very similar. Now, before with the upper and lower sums, we were calculating the area under the curve. And we can do the same thing here with our indefinite integrals, but you will notice that for this example, because our answer was a -3, that can certainly not be representing the area under a curve due to the negative. And in future videos, we'll look at how we can handle calculating the area using indefinite integrals. So keep in mind, it is okay to have a negative as long as you're not calculating the area underneath a curve. So if you need to, go back and review some of those upper and lower sums, and if you look at the video, you'll realize that this is the same limit definition we did before, and we're just applying it to our indefinite integrals. And in the future, we're going to look at another technique to make this a little bit easier.